Welcome to Civil Engineering Edge, your dedicated hub for engineering knowledge, innovation, and real-world applications. In today's video, we unlock how AI-powered sensors are quietly protecting the world's bridges from catastrophic failures. As infrastructure ages and traffic loads increase, traditional inspections are no longer enough. That's where cutting-edge structural health monitoring steps in combining sensors, AI, digital twins, and predictive analytics to safeguard public safety. Whether you're a civil engineering student, a practicing professional, or someone fascinated by modern infrastructure, this video will give you a clear and powerful understanding of how smart technology is reshaping structural safety. Introduction: the silent sentinels of our structures. The problem with aging infrastructure across the world. Thousands of bridges that were built decades ago are now approaching the end of their design life. These structures have endured continuous traffic loads, harsh environmental cycles, corrosion, material fatigue, and in many places, inadequate maintenance. Traditionally, engineers have relied on periodic manual inspections to assess their condition. Although visual checks and simple measurements provide valuable information, they are fundamentally limited. Inspectors may miss early, microscopic signs of damage that lie beneath the surface cracks inside girders, hidden corrosion in tendons, or subtle changes in vibration responses that indicate weakening. Inspections are also carried out infrequently, sometimes once every few years, meaning potential problems can grow unnoticed between visits. In addition, human judgment can be subjective, varying from person to person depending on experience. As traffic loads continue to rise and extreme weather events become more frequent, the risk associated with aging, overstressed infrastructure increases significantly. A minor undetected flaw can escalate into a catastrophic failure if not repaired in time. This growing concern has pushed engineers around the world to rethink how we maintain bridges. The need is clear. We require continuous, accurate, data-driven monitoring that can detect problems early, long before they become visible or dangerous. The SHM revolution, structural health monitoring, or SHM, represents a major shift from traditional inspection-based maintenance to a smarter, more proactive approach. SHM systems use distributed sensors, data acquisition units, and analytical tools to continuously track the health of a bridge. Instead of relying solely on periodic human inspections, SHM provides real-time insights into how a structure behaves under actual loads. Parameters such as strain, vibration, tilt, displacement, temperature, and humidity can be tracked 24/7, allowing engineers to detect unusual patterns or deviations from expected behavior. This enables maintenance teams to intervene early, often preventing failures long before they pose threats. SHM also helps engineers understand long-term performance, aging patterns, and the effectiveness of past repairs. Most importantly, SHM turns a bridge into a self-reporting system, a structure that can talk by sending signals about its internal health. This revolution is transforming civil engineering asset management, making it more efficient, cost-effective, and safer. By integrating SHM into modern infrastructure, cities and governments can prolong the lifespan of existing bridges, optimize maintenance budgets, and drastically reduce the chances of unexpected failures. SHM is not merely a technology upgrade, it is a shift toward data-driven decision-making and sustainable, resilient infrastructure management. A glimpse into the future with AI plus sensors. The future of bridge safety lies at the intersection of sensors and artificial intelligence. Today's SHM systems are evolving beyond simple data collection. With AI-powered analytics, bridges can now interpret their own sensor data, detect anomalies automatically, and even predict upcoming failures before they occur. Machine learning algorithms can analyze vibration signatures, temperature trends, strain variations, and traffic-induced responses to recognize patterns that humans might miss, instead of waiting for visible cracks or deformation. AI can identify the earliest indicators of material fatigue, loosening joints, or weakening supports. This transforms maintenance from reactive to predictive. Problems are addressed before they escalate. Future bridges will operate like intelligent organisms, continuously sensing their environment, learning from data, and warning engineers when intervention is needed. With the rise of 5G, IoT, cloud platforms, digital twins, and edge computing, SHM systems will become faster, more accurate, and more interconnected. Cities may soon operate smart infrastructure networks where each bridge, tunnel, and building communicates its health status in real time. For engineers, this means safer structures, reduced downtime, and smarter asset management. For society, it means fewer collapses, improved public safety, and sustainable use of resources. The future is proactive, predictive, and powered by AI-driven SHM. The bridge's nervous system, smart sensors and data collection, types of sensors. Modern structural health monitoring systems use a wide range of sensors, each designed to capture a specific type of physical response within the bridge. Together, these sensors act like the nervous system of the structure, continuously collecting data that reflects its health. Strain gauges monitor stress and deformation in critical members, offering insights into load distribution and material fatigue. Accelerometers detect vibrations caused by traffic, wind, or seismic events, helping engineers identify dynamic behavior changes. Displacement sensors and tiltmeters track tiny movements, rotations, and shifts in the structure that might indicate settlement, cable loosening, or girder deflection. Acoustic emission sensors are highly sensitive to high-frequency waves produced by crack initiation and propagation deep inside materials. Environmental sensors measure temperature, humidity, wind speed, and water levels, helping correlate structural responses with changing climate conditions. Some bridges also use corrosion sensors to detect chloride penetration, pH changes, or steel section loss in reinforced concrete and steel members. Fiber optic sensors, including FBG fiber Bragg grading systems, offer long-distance, highly accurate monitoring for strain, temperature, and vibration. By integrating all these sensors, engineers gain a holistic, real-time view of bridge behavior. This multi-sensor approach transforms a bridge into a self-monitoring, intelligent structure. Strain gauges. Strain gauges are among the most fundamental and widely used sensors in structural health monitoring. They measure strain, which is the deformation a structural element undergoes when subjected to external loads. When vehicles move across a bridge, its beams, decks, and supports bend slightly. Strain gauges record these minute changes, typically in microstrain units. A standard strain gauge consists of a thin metallic foil arranged in a grid pattern. As the material it's attached to either stretches or compresses, the foil deforms, changing its electrical resistance. This change is recorded and translated into strain values. Engineers place these sensors at critical stress points such as mid-span regions, support zones, joints, or near welds to monitor how loads are distributed. Strain gauges help detect early signs of material fatigue, overloading, and long-term creep. In composite and steel bridges, they are essential for evaluating performance under increased traffic. In press-stressed concrete bridges, they help track tendon force losses. Modern SHM systems use both electrical and fiber optic strain gauges, the latter offering higher durability and resistance to environmental conditions. Through continuous strain monitoring, engineers can recognize abnormal patterns, verify design assumptions, and ensure that structural elements are functioning safely over time. Accelerometers. Accelerometers play a crucial role in understanding the dynamic behavior of bridges. These sensors measure acceleration, which represents how quickly the speed of a vibrating element changes over time. Bridges continually vibrate under traffic loads, wind, and thermal variations. But during extreme events like earthquakes or storms, vibrations increase significantly. Accelerometers capture these dynamic responses, helping engineers identify changes in modal properties such as natural frequencies, mode shapes, and damping ratios. These parameters are vital because a shift in natural frequency can indicate the development of structural damage, stiffness loss, or deterioration. Modern accelerometers come in several types, including piezoelectric, MEMS-based microelectromechanical systems, and high-sensitivity broadband models. MEMS accelerometers are commonly used due to their compact size, low power consumption, and ability to capture high-frequency data. Installing multiple accelerometers across decks, towers, cables, or piers allows engineers to track how vibrations propagate through the structure. Accelerometers are especially important in cable-stayed and suspension bridges, where wind-induced vibrations and cable oscillations must be controlled. In seismic-prone regions, they help assess real-time earthquake impact and post-event health. By continuously measuring vibration characteristics, accelerometers provide essential data for both everyday monitoring and extreme event evaluation. Displacement and tiltmeters. Displacement sensors and tiltmeters provide essential insights into the physical movement and alignment of bridge components. Displacement sensors, such as linear variable differential transformers (LVDTs), laser displacement meters, or GPS-based units, measure the relative movement between two structural points with high precision. These measurements reveal deflection patterns, expansion joint behavior, and long-term settlement of piers or abutments. Even small shifts in millimeters can indicate structural weakening or unusual load redistribution. Tiltmeters, on the other hand, measure angular rotation. They detect changes in inclination, allowing engineers to monitor rotations in bridge piers, towers, bearings, or decks. A tilt in a pier might indicate scour, foundation settlement, or seismic effects, while rotations in towers of cable-stayed bridges may reflect cable tension imbalances. When combined, displacement sensors and tiltmeters create a detailed picture of the bridge's geometric behavior. They help verify whether structural elements are moving as expected or deviating from design predictions. Long-term monitoring of displacement trends also helps detect thermal movements, creep, and shrinkage effects. During extreme conditions, such as floods or earthquakes, these sensors provide real-time alert data that helps engineers take immediate action. Overall, they ensure that subtle yet critical structural shifts do not go unnoticed. Acoustic emission sensors. Acoustic emission sensors offer a powerful way to listen to the internal health of bridge materials. When a structural component experiences stress, microscopic cracks may form or existing cracks may propagate. These processes release high-frequency elastic waves that travel through the material. Acoustic emission sensors detect these waves and convert them into electrical signals that can be analyzed. Unlike visual inspection or surface-level measurement, acoustic emission sensing allows engineers to identify internal damage that is invisible from the outside. This makes them especially valuable for steel bridges, press-stressed concrete members, and composite structures where internal defects pose significant risks. Acoustic sensors can detect events such as fiber breakage, rebar corrosion, weld failures, fatigue crack growth, and delamination. When several sensors are placed throughout the structure, engineers can triangulate the exact source of the emission, enabling precise localization of damage. Acoustic monitoring is highly sensitive and useful for capturing sudden changes, making it ideal for critical components under heavy loads. The real-time nature of acoustic emission systems allows maintenance teams to respond quickly if active cracking is detected. By continuously listening to the sounds of structural distress, these sensors provide an early warning system that significantly enhances bridge safety. Environmental sensors. Environmental sensors play a key role in understanding how external conditions influence bridge performance. These sensors measure parameters such as temperature, humidity, wind speed, rainfall, fog levels, and water levels near piers. Because environmental factors directly affect materials and structural response, tracking them helps engineers quantify and isolate their impact. Temperature sensors, for instance, monitor thermal expansion and contraction, which can cause significant movement in long-span bridges. Humidity sensors help detect conditions that accelerate corrosion in steel components or moisture ingress in concrete. Wind sensors are crucial for understanding aerodynamic effects, especially in suspension and cable-stayed bridges where wind-induced oscillations can lead to instability. Water level sensors near river bridges monitor flood conditions, scour potential, and foundation vulnerability. Environmental sensors also support predictive maintenance by correlating environmental stressors with structural degradation rates. For example, bridges in coastal zones may experience faster chloride-induced corrosion, while bridges in cold climates are affected by freeze-thaw cycles. By integrating environmental data with structural data, engineers can build accurate predictive models that account for weather patterns and climate exposure. Overall, environmental sensors ensure that SHM systems do not just react to structural changes, but also understand the external forces driving them. The IoT advantage. The Internet of Things IoT has transformed structural health monitoring by enabling real-time connectivity between thousands of distributed sensors and a central monitoring platform. Traditionally, sensor data had to be manually collected or stored locally, limiting the amount of information available for timely decision-making. IoT eliminates this barrier by allowing sensors to communicate wirelessly through low-power networks such as LoRaWAN, NB-IoT for G, 5G, or Wi-Fi. Each sensor becomes a smart node capable of sending live data streams to cloud servers or on-site gateways. This interconnected ecosystem enables large-scale monitoring, even across long-span bridges or complex multi-bridge networks within a city. IoT significantly reduces wiring needs, installation time, and maintenance complexity. It also allows remote access, enabling engineers to monitor bridge conditions from anywhere in the world through dashboards and mobile apps. Smart IoT platforms can automatically trigger alerts when sensor readings exceed thresholds, improving response time. The integration of IoT also allows for edge analytics, where basic data processing happens near the sensor to reduce bandwidth and increase efficiency. Overall, IoT makes SHM more scalable, cost-effective, and capable of providing continuous insight into structural behavior, laying the foundation for future AI-driven predictive maintenance. Data acquisition and transmission. Data acquisition and transmission form the backbone of any SHM system. The process begins with sensors capturing raw physical responses: strain, acceleration, temperature, displacement, and more. These signals are then fed into Data Acquisition Systems DAS, which can be centralized or distributed across the bridge. The DAS converts the analog signals from sensors into digital data that computers can interpret. It also filters noise, synchronizes timing, and ensures data accuracy. Once digitized, the data is transmitted either to cloud platforms or to local edge computing devices for immediate processing. Transmission methods vary depending on the project's design. Wired fiber optic networks for high bandwidth applications, wireless IoT modules for low power systems, or hybrid configurations for long-span bridges. Edge computing devices located near sensors can run real-time algorithms to detect anomalies instantly, reducing latency and enhancing safety. Meanwhile, cloud-based systems store large volumes of historical data for long-term analysis, model calibration, and AI-driven prediction. Redundancy and encryption ensure data security and reliability by enabling fast, accurate, and uninterrupted data flow from the bridge to analytical systems. Data acquisition and transmission ensure that SHM platforms deliver actionable insights that support timely maintenance decisions and continuous structural safety. The brain of the operation. AI and machine learning analysis. From data to insights, modern SHM systems capture massive quantities of data, every second strain readings, vibration records, temperature variations, tilt changes, acoustic emissions, and environmental measurements. For a large bridge with thousands of sensors, this quickly adds up to millions of data points per day. Manually reviewing such a volume is practically impossible for humans. This is where artificial intelligence becomes essential. AI algorithms organize, clean, and interpret raw data, transforming it into meaningful insights. First, AI filters noise, removes outliers, and corrects missing data to ensure accuracy. Next, the system identifies trends, patterns, and correlations that would otherwise go unnoticed, such as how temperature affects strain readings or how traffic loads influence vibration modes. AI processes the data continuously, allowing real-time understanding of how the structure behaves under various conditions. Instead of relying solely on thresholds or fixed rules, AI learns the normal behavior of the bridge through large training datasets. Once the system understands the structure's baseline patterns, it can automatically detect deviations and alert engineers. By handling data at this scale and speed, AI converts raw sensor streams into clear, actionable insights that support smarter maintenance decisions, reduce risks, and ensure bridges remain safe throughout their operational life. Machine learning at work. Machine learning forms the core of intelligent SHM analysis. It enables computer systems to learn from data, adapt to new patterns, and improve their performance without being explicitly programmed. Several types of machine learning are applied in bridge monitoring. Supervised learning is used when historical labeled data is available, allowing the model to learn relationships between sensor inputs and known structural conditions. For example, models can be trained to classify stress levels or identify impact events. Unsupervised learning helps when data is unlabeled. It identifies clusters, correlations, and hidden patterns within the data, making it ideal for anomaly detection in long-term monitoring. Reinforcement learning can assist in optimizing maintenance schedules by learning which actions lead to better structural performance over time. Machine learning is also used to analyze modal properties, detect early fatigue, classify cracks based on acoustic signatures, and correlate environmental data with structural responses. Deep learning models, especially neural networks, can process large, complex datasets, such as full vibration time histories or temperature strain relationships. These models identify subtle changes that traditional methods may overlook. By employing machine learning, SHM systems evolve into intelligent, adaptive platforms capable of understanding the unique behavior of each bridge. Anomaly detection. Anomaly detection is one of the most critical AI applications in structural health monitoring. The principle is simple. The system first learns what normal looks like, then continuously checks for deviations. Machine learning models analyze large volumes of past sensor data to understand typical behavior patterns such as normal vibration frequencies, strain ranges under daily traffic, temperature-induced displacement, or environmental response cycles. Once this baseline is established, the model monitors incoming real-time data and flags any unusual patterns. For example, an unexpected drop in natural frequency might suggest stiffness loss due to cracking. A new vibration peak could indicate loosened bolts or cable tension imbalance. Sudden increases in acoustic activity may signal crack propagation. Tilt changes beyond typical thermal movement might reflect foundation settlement. Anomaly detection systems use advanced algorithms such as clustering, autoencoders, neural networks, or statistics-based approaches to determine whether new data fits within expected ranges. When an anomaly is detected, engineers receive alerts along with visualizations that pinpoint the sensor location and suspected cause. This early warning capability is invaluable because it identifies problems long before they become visible or serious. Anomaly detection helps prevent failures, reduce downtime, and extend the lifespan of vital infrastructure. Anomaly detection. Failure prediction, predictive analytics. Predictive analytics elevates SHM systems from simple monitoring tools to powerful forecasting platforms. Instead of reacting to problems after they appear, AI models can estimate when a component is likely to deteriorate or fail based on historical data, real-time trends, and environmental conditions. The process begins by collecting long-term sensor data strain readings, displacement trends, corrosion rates, vibration signatures, and environmental stressors. Machine learning models analyze how structural elements degrade over time and identify patterns that precede failure, such as gradually increasing deflections or repeated acoustic bursts. Using statistical techniques, regression models, neural networks, or time series forecasting, AI predicts future behavior and estimates the remaining useful life of structural components. These predictions help engineers plan timely maintenance, allocate budgets efficiently, and avoid emergency repairs. Predictive analytics is especially important for aging bridges where life extension strategies are crucial. It also supports decision-making after extreme events like earthquakes or floods, helping engineers determine whether a structure requires immediate repair. The goal is to transition from a reactive maintenance culture to a proactive, cost-efficient system. By forecasting future risks, predictive analytics enhances safety, reduces operational costs, and ensures that bridges remain dependable for years to come. Edge computing. Edge computing is an essential enhancement to modern SHM systems because it allows real-time data processing directly at or near the bridge. Instead of sending all sensor data to the cloud, which can cause delays or require large bandwidth, edge devices analyze critical information locally. These compact, high-performance processors are installed within the monitoring system, often inside control cabinets or sensor hubs on the bridge. They run algorithms that filter noise, compute vibration modes, detect anomalies, or evaluate structural responses instantly. For events requiring immediate reaction, such as seismic activity, sudden tilting, or active cracking, edge computing dramatically reduces the response time by bypassing cloud latency. If a critical threshold is exceeded, edge devices can automatically trigger warnings, activate alarms, or send high-priority notifications to engineers. They also decide which data is important enough to upload to the cloud and which can be discarded, optimizing bandwidth and storage usage. Edge computing enhances reliability by ensuring the system continues to function even in areas with unstable internet connectivity. When combined with AI models embedded at the edge, the bridge becomes a self-diagnosing structure capable of taking intelligent actions in real time. This makes SHM systems faster, smarter, and more efficient than ever. Advanced techniques, digital twins, and visual inspection. Digital twins. Digital twins represent one of the most advanced developments in structural health monitoring. A digital twin is a highly detailed, virtual model of a bridge that updates in real time using live sensor data. Every strain reading, vibration pattern, displacement measurement, and environmental change is synchronized with the digital replica, allowing engineers to visualize exactly how the structure behaves under varying conditions. Built using finite element models, BIM data, and historical performance records, the digital twin mirrors the physical bridge's geometry, materials, and dynamic response characteristics. Engineers can simulate scenarios such as extreme traffic loads, temperature fluctuations, or seismic events to see how the bridge would react before these events occur in real life. The platform also enables what-if analyses, testing potential repair strategies, evaluating deterioration progression, or assessing the effects of retrofitting, all in a risk-free virtual environment. Because digital twins continuously evolve with incoming data, they create a living model that reflects the structure's health at any moment. This technology supports predictive maintenance, life cycle assessment, and decision-making by providing deeper insights into structural behavior. Ultimately, digital twins empower engineers to manage infrastructure more efficiently by combining real-time monitoring and advanced simulation into a single integrated tool. AI-powered visual inspection. AI-powered visual inspection revolutionizes how engineers detect surface-level damage on bridges. Traditionally, visual inspections required teams to physically access each part of the structure, often using scaffolding, rope access, or under-bridge vehicles. These methods are time-consuming, costly, and sometimes risky. With drones equipped with high-resolution cameras and LiDAR sensors, inspections become faster and safer. Drones can reach difficult locations such as the underside of decks, tall towers, or narrow expansion joints without disrupting traffic. The captured images and 3D scans are analyzed using computer vision algorithms that automatically identify cracks, spalling, corrosion patches, rust stains, delamination patterns, and deformation. AI models are trained on thousands of defect images, enabling them to detect even hairline cracks with exceptional accuracy. These systems can measure crack width, track growth over time, and classify severity levels. Thermal imaging drones can also detect subsurface voids or moisture ingress that are invisible to the human eye. The combination of drones and AI greatly reduces inspection time while improving consistency and objectivity. Engineers receive annotated images, defect maps, and condition reports almost instantly. By automating visual inspections, AI enhances the reliability of bridge assessments, supports better maintenance planning, and significantly increases safety for both inspectors and the public. The outcome: proactive maintenance and enhanced safety. Beyond reactive repairs, for decades, bridge maintenance followed a mostly reactive approach. Problems were addressed only after cracks became visible, components showed distress, or failures occurred. This method not only increased risks, but also resulted in higher repair costs and lengthy disruptions. With modern SHM systems and AI analytics, the philosophy of maintenance has fundamentally changed. Instead of waiting for deterioration to develop, engineers now receive early warnings based on real-time data patterns. Predictive indicators such as unusual strain responses, subtle vibration shifts, or acoustic emissions alert maintenance teams long before damage becomes critical. This allows targeted interventions at the most effective time, preventing failures and extending the structure's lifespan. Proactive maintenance also ensures that small issues do not escalate into structural crises. Continuous monitoring reveals how a bridge behaves under daily traffic, temperature cycles, and environmental forces, providing a complete performance history. Engineers can plan restorations based on actual structural needs rather than fixed schedules or visual guesswork. The shift from reactive to proactive maintenance marks one of the biggest advancements in modern civil engineering, lowering risks, improving safety, and enabling smarter asset management. Bridges become not just monitored, but intelligently maintained throughout their operational life. Optimized resource allocation. One of the greatest advantages of AI-driven SHM systems is their ability to help infrastructure managers allocate resources more efficiently. Traditionally, maintenance budgets relied on periodic inspections, subjective judgments, and broad assumptions about structural condition. This often resulted in unnecessary repairs on healthy structures while genuinely deteriorating components were overlooked. AI transforms this process by ranking structural elements based on real-time risk assessment, deterioration trends, and predictive failure timelines. By analyzing thousands of data points simultaneously, AI systems can identify which parts of a bridge require immediate attention, which can be scheduled later, and which remain safe. This prioritization reduces unnecessary expenditure and ensures that funds are directed exactly where they are needed. Predictive analytics also enables long-term budgeting by forecasting when future maintenance will be required, helping agencies plan ahead instead of reacting to emergencies. Moreover, targeted interventions reduce downtime, preventing traffic disruptions and minimizing economic losses. When combined with digital twins and automated reports, decision-makers gain a clear visual understanding of maintenance priorities. The result is a highly optimized maintenance ecosystem where safety improves, costs decrease, and long-term sustainability becomes achievable. Real-world success stories. Around the world, many iconic bridges have already adopted advanced SHM and AI technologies, demonstrating their effectiveness in real-world conditions. Major suspension bridges, long-span cable-stayed bridges, and vital transportation links rely heavily on continuous monitoring due to their complex behavior and high traffic demands. For example, prominent landmark bridges such as the Golden Gate Bridge in the United States and the Hong Kong-Zhuhai-Macau Bridge in China have implemented extensive sensor networks to track structural responses such as wind loads, cable forces, vibrations, and temperature effects. These systems allow engineers to evaluate performance during storms, heavy traffic, or seismic activity. In several regions, AI-assisted drone inspections have identified cracks on steel and concrete surfaces that traditional inspections had missed. Long-span bridges exposed to marine environments now use acoustic emission sensors and corrosion monitoring systems that feed directly into predictive analytics platforms. These real-world applications prove that AI, digital twins, and sensor-based monitoring are not experimental concepts. They are practical tools ensuring the safety of millions of daily commuters. The success of these systems continues to inspire global infrastructure agencies to adopt SHM technologies, paving the way for safer, smarter, and more resilient bridge networks worldwide.
Conclusion: building a more resilient future. Expanding beyond bridges. While bridges are among the most visible beneficiaries of AI-powered structural health monitoring, the same technologies are transforming many other categories of critical infrastructure. High-rise buildings now integrate sensor networks that track sway, interfloor drift, wind loads, and foundation settlements, especially in seismic zones. These real-time insights help structural engineers refine performance-based design and plan timely retrofits. Dams, particularly aging concrete gravity dams and embankment structures, utilize strain gauges, pore pressure sensors, seepage monitors, and acoustic systems to detect leakage, cracking, and long-term deformation. In tunnels, fiber optic sensors, convergence meters, and environmental systems measure lining, stress, groundwater pressure, and ventilation efficiency, ensuring safety for vehicles and metro systems. Even offshore structures such as oil platforms and wind turbines rely on vibration, monitoring, and corrosion sensors to withstand harsh marine environments. AI enhances the interpretation of these datasets, predicting aging patterns and identifying failure risks early. Across all these applications, digital twins and real-time dashboards provide engineers with a unified view of structural performance. The expansion of SHM into diverse infrastructure types marks a major shift from reactive maintenance towards predictive, data-driven asset management. Ultimately, these technologies create safer, more reliable, and longer-lasting structures across entire cities and national networks. The human element, as advanced as AI sensors and digital twins have become, the human role in infrastructure management remains irreplaceable. Engineers bring deep domain knowledge, design experience, ethical judgment, and contextual understanding qualities that technology alone cannot replicate. AI functions as a decision support system, helping professionals process enormous amounts of data, identify patterns, and predict failures with unprecedented accuracy. However, interpreting the data, evaluating risks, and making final decisions still rely heavily on engineering expertise. Human intuition, especially during emergencies or unexpected events, continues to be vital. AI may flag anomalies or deterioration trends, but determining the severity, planning repair strategies, and balancing safety with cost considerations are human responsibilities. Additionally, engineers design, calibrate, and validate SHM systems to ensure that AI models are accurate and reliable. They also consider social, environmental, and economic factors that algorithms cannot fully comprehend. Rather than replacing engineers, AI empowers them by reducing workload, enhancing situational awareness, and enabling faster, more informed decisions. The future of infrastructure resilience depends on a strong partnership between human expertise and intelligent technology, where each complements the other to achieve safer and more efficient outcomes.
A safer world. The integration of AI, sensors, and advanced monitoring tools marks a pivotal moment in the evolution of civil infrastructure. These technologies provide continuous visibility into the health and performance of bridges, buildings, tunnels, dams, and other assets, essentially giving them a digital heartbeat. By detecting early signs of distress and predicting potential failures, SHM systems significantly reduce the risk of catastrophic collapse. This proactive approach not only protects human lives, but also prevents costly repairs and long disruptions to transportation networks. Real-time monitoring ensures that maintenance teams respond quickly and effectively, focusing resources where they are needed most. The long-term impact is profound. Infrastructure lasts longer, operates more safely, and requires fewer emergency interventions. Communities benefit from reliable transportation, uninterrupted services, and improved disaster resilience. As digital twins, IoT networks, and AI analytics continue to advance, future infrastructure will become increasingly intelligent and self-aware. Ultimately, this technology contributes to creating a safer, smarter, and more sustainable world, one where civil engineering decisions are informed by real-time data, predictive insights, and a deep understanding of how structures behave. By embracing SHM and AI, we build not just stronger structures, but a more resilient future for generations to come. Thank you for watching this deep dive on how AI and sensors are revolutionizing bridge safety here on Civil Engineering Edge. As we've explored, intelligent monitoring isn't just the future, it's already transforming the way engineers maintain critical structures worldwide. If you found this video informative and want more content on civil engineering concepts, structural innovations, and real-world applications, make sure to like, share, and subscribe. Your support helps us reach more learners and professionals. Stay tuned for upcoming videos where we continue to simplify complex engineering technologies for everyone. Until then, stay curious, stay safe, and keep learning with Civil Engineering Edge.